Okay, we are nearing the end of the semester, thankfully, from all of us. I wish we had a longer vacation coming up, but it is what it is. We are finishing up the last of the lab problems, and there we go. Today we're going to be doing the non-parametric statistics. Please remember, as always, to get all that stuff you need beforehand. So the data sheets for each of these programs for the lab, calculator, you're going to need your critical value tables this time. I don't have those sort of up and available for you. So certainly, given what we know about these particular critical value tables, knowing which one to use is something that you should also have. And as always, please work through these. Don't just rely upon the answers showing up, because really we'll have just the one chance on the final homework to do the non-parametrics. And then the exam follows just really a weekend and a half after that. So let's do the non-parametrics again. Hopefully you've gone through the first video already, and you can sort of see why this one is a little bit more dicey in terms of knowing what to do. So if there's one or two of you who are just sort of doing the lab days but not the classroom days, trust me, the non-parametrics are a bit more chaotic, and knowing what to do and how to get there from the formulas a little bit trickier. So even though it's like an hour and a half, go back and watch the other one, because that has really all the information on it. And of course, the most obvious F-bomb I've ever dropped on camera. So fantastic. Okay, so let's go forward with this one. We'll start with the chi-square. Again, remember, on homework and on exam day, it's not telling you which one this is going to be. So that new thing is now we're going to sort of throw all the information together. And part of your job is to figure out which one you're supposed to choose, what statistic to choose to analyze. So that has to be part of your studying as well for the final. Again, no notes, no books, no videos, no nothing when we get there. Also, a final reminder, if you are one of the people who did not successfully figure out how to upload and send me your homework number 6, you're going to need to get that fixed for this final homework. So try to send me something, or at least try to figure out how to make it work, because you will have to send me the final homework and then the exam, because there's no way to get it to me before grades are due for either one of those. And the final homework's going to take actually about 3 times as long to grade as compared to the final exam. So I don't have the luxury of waiting for this to get to me. So you're responsible. I sent the link and the app information to you. Make sure that you have that down before we get to the 20th, which is when when the final homework will be due. Okay, so today we're doing the chi-square first, and this time I put up more of a description. The last time I just sort of went through the problem. So sweetbriar equestrians are having a struggle. It's 2020, of course. Why would they be off the hook compared to the rest of us? A QV left some Red Bull in the stables, and now they're all sort of hyped up. People are getting tossed off left and right, and someone sort of says that horses are susceptible to psychosis, depending on depending on the skill level of the rider. And Mimi sort of sets you into action to see if there's a relationship between the kind of horse and the rider, concerning these animals are all hopped up on Red Bull. Again, the varsity getting a little bit more training than the regular rider, who's basically told, just hold on. I'm doing this from my knowledge of riding programs, so whatever. All right, remember that with the chi-square, we're working with all nominal data, and this is where we are going to be starting. So the idea here is the breed of horse. I will say I went through creating this with the best of intentions, and then I realized I didn't know what the hell different horses were. So we're just going to go with this. And it's that point of semester where I'm as tired as you are. So we have 3 groups of horses. I'll assume these are close to correct: ponies, brown horses, and ones that look like goats. I don't know. I guess Clydesdale would have been a third one, but I couldn't spell it. And then regular people or varsity riders, because we do know the varsity riders are better than the rest of us. That's what we've been told. Okay, so you're not getting a lot of help from me. This is just me running through the responses with you, but being here for the steps to give you a chance to catch up. So step 1, solving the row and column totals, and of course that intersection there as well to get the total number of participants in this cell, and then creating the chi-square table. and entering this data in. So really just the first two columns is where I'm expecting you to get from, which again is taking these and identifying them down to at the bottom. So go ahead and get started on this and double check at the point you have that solved and those columns done. Check back and see how we are doing. All right, let's see. So let me close this up here for just a moment. So the column totals 200, 100, 300, and then 100, 100, 100 going across. Now our next step 2, is going to be calculating the expected values. And for each of these cells that we have up here or down here, you are going to fill or solve for each of these individual expected values. Whatever cell we're talking about, row, so if this is the one we're doing varsity riders on brown horses, it is going to be row total 100 multiplied by column total of 100 divided by total number of 300 here to get that value, and do that for each and every one of these and to go ahead and solve for that. All right, now again, because we have a lot of overlap here, these columns are all the same. Not surprising we're going to have values that look like this. So for any one of these, so for like this one, it was 200 multiplied by 100 divided by 300. For this one, this 39, row total 100 multiplied by column total 100 divided by 300. So these should have been the answers that you got. So 66.67s and then 33.33s for the rest of them. Okay, now finish the table. So the next steps are things that you should be able to do. We're going to create a difference column first, square the difference column, and then do the final calculation, d squared divided by the expected value. And again, we walked through this before, so you should know that. And then go ahead and solve for the chi-square, which is just the sum total of this last column. So go ahead and do all of that and come back and check your answer. All right, let's see how we did. And in this case, we have scores that are like this. So for our first one, which is regular human on ponies, our expected value was 66.67. The observed value was 58. So to get a different score, 58 minus 66.67 gives us a value of negative 8.67. We square that value to give us 75.17. Remember, we square things because it gets rid of the negative value. And of course, it keeps the same proportional distance between it. Then we take our difference score value to get to the last column, divided by the appropriate expected value. So 75.17 divided by the expected value of 66.67 should give you 1.13. Second one, I'll just run through one more. The observed value for a regular person on brown ponies or brown horses, we expected 81, we got 66.67. 81 minus 66.67, 14.33. Square that value to get the d squared column, 205.35. And then divide this value, the d squared, by the expected, 66.67, and that gives us 3.08. Okay, so the next step would be to sum that last column up. Again, I guess I stopped here and turn this into step 4, simply to make sure that you have these values right before you add them up. If everything looks good, go ahead and solve for chi-square, which is again the addition of this last column. Go to the chi-square table, determine the critical value, make a judgment about whether or not this is statistically significant, and then try to interpret. Again, remember we are limited with what we can say on the chi-square, but go ahead and do your best and then come back and compare your answers. Okay, so our chi-square table is, I'm sorry, I guess I did put these in. I'm a better person than I expected to be. You should know that I did these things over some of these things I knew were coming over the summer, so I really did kind of forget what things I kept in, which things I didn't. So degrees of freedom, k minus 1 multiplied by q minus 1, number of categories in each of these groups, or number of levels in each of those categories. So we had 3 kinds of ponies, so 3 minus 1 is equal to 2, multiplied by the 2 kinds of rider. 2 minus 1 is equal to 1, so 2 times 1 is equal to 2. So we have 2 degrees of freedom, and we have 0.05 as our alpha level. So we go across, and I don't know why I keep using this one. This is how the last one ended up as well. Our critical value is 5.991. Okay. Our obtained value when you added up that last column of scores was 14.07. So a chi-square with 2 degrees of freedom is equal to 14.07. Our value is greater than the critical value, so this is significant. So P is less than 0.05. There does appear to be a relationship between breed of horse and skill of rider based on the number of concussions, which again, any interpretation going back to the setup in the original question. All right, so that should be your answer. Chi-square, 2 degrees of freedom, 14.07. P is less than 0.05. If that is not your answer, go back and figure out where the mistakes were made, because these things, again, can serve as the study guide. That's why we're doing these in lab rather than what we've normally done in lab over the years. Okay, next one, Mann-Whitney. So shake it off. Let's move into the Mann-Whitney. This is our correlate to the independent samples t-test. So we have 2 groups, but it is non-parametric, so something has gone wrong or blankety, blankety, blank. Okay, next page is a small data set listing the ages at which a small sample of patients are given a diagnosis of type 2 diabetes. Is there any difference between the genders in these ages? That's sort of a poorly written question. It should be the ages at which these genders get diagnosed with diabetes. So we're going to have a list of sort of like a level of sort of like blood sugar is what I would expect, split up for the males and the females. So remember with this one, again, this is a corollary to our independent sample t-test. So we have just two groups. We're going to try to see if there's a difference between these 2 groups. As it's non-parametric, as we have done in the previous video, we're going to start by summing everything up. We're treating this as one entire group. So do the rankings on these first, and then go ahead and sum those column totals. Remember, we're treating this entire sample as one group, not ranking the males and ranking the females as separate entities. They're all combined as people when we do the rankings. Again, doesn't matter which one has the one, okay, where you start at the lowest score or the highest score, just be consistent and you will be fine. So rank the samples and then sum things up and come back and see where we stand. All right, let's see. So you should have received a rank for the male columns of 32 and a ranking for the female columns of 13. Again, if you sort of look at this, how this ends up, the one that has the lower number tends to have the lower rank. So if they're clustered all together, like the 4 lowest scores were in the female group and then the next 5 scores were in the male group, that would be the highest percentage we could actually get, the farthest separation we could get. So it didn't quite work out that way. It wasn't the lowest 4, but more of the low ones look like they're in the female group as compared to the male group. So if we did a mean, for example, the scores would be lower on the female side than the male. Of course, I've covered this up. So here's our U formula. So we got one for the male group, one for the female group. The dog just tried to get in, but I barricaded it this time so he couldn't. So solve for U1 and U2. And remember, as part of the solution to this, you're going to have to figure out the ends of each group. Really not that difficult to do. And the overall sample size for this. Again, in this formula, this 2 down here is a constant. We're sort of doing a mean value for this. So go ahead and solve for U1 and U2, and then come back and check. All right, let's go ahead. So we plugged this in. There were 5 in group 1, 4 in group 2. So our total number was 9. N1 number in group 1, 5 multiplied by the number in group 2, 4 plus number in group 1, 5 multiplied by 5 plus 1 divided by 2. Quantity, close that, and then subtract from all of that the ranking, summed rank of 32. And then obviously changing the numbers around here for the second group. And you get that. When you solve for this, you should get a U1 score of 3 and a U2 score of 17. Now, remember, we have 2 scores. So what did we do last time we had 2 scores? Okay, we're going to choose one of them. And in this case, we choose the one that has the lowest value. So we're going to be choosing 3 as the value that we go forward with. Okay, so step 5, 6, and 7, figure out the critical value for this, put the calculation in the final format, and interpret the finding that you have. Okay, so go ahead and do that, and then start back up when you are ready. Okay, let's see how we did. So in this one, our critical value is based on the scores of 5 and 4, 5 people in one group, 4 in the other. So we start off here with 5, go down for 4, and the 0.05. Okay, so it's this block, but 0.05 here is a value of 1. So our critical value is 1. We use the calculated value of 3 in this. So we know that that's our calculated value. And remember with this one, this is one of those two places where we have the flip in terms of how we do the critical value. So for it to be significant, our obtained value has to be smaller than the critical value for this to be significant. So U with 5 and 4, which is, it's really not degree of freedom, it's sample size, but it's treated the same way in writing it out, is equal to 3, the lowest of those two values we calculated. Because this is greater than the critical value, this is, again, the one where the decision is switched, this is not significant. Okay? Remember on this one, it has to be under the critical value for it to be significant. So P with 5, or I'm sorry, U with 5 and 4 is equal to 3. P is greater than 0.05. There is no apparent difference in the age of diagnosis for the sample of patients between the males and the females. Okay. Dun, dun, dun. I understand why you guys watch the lab videos, because they go a hell of a lot quicker than the other ones do, but the other ones have all the information. So just on these, trust me, you want to make sure you know where all this is coming from. So make sure you watch the other one before you are here. All right, the Wilcoxon, the next one. And this is, of course, the one on the last video where we all sort of collectively, I think, lost our minds. Because this is like the 2020 formula with all the weirdness that's thrown into it. So let's look at the Wilcoxon and this particular data set. So here's our setup of the question. You're an elementary school teacher with a group of kids who are a little bit rowdier than normal. You develop a training program to implement in your classroom. You score them on a level of activity. You then do the training, check them afterwards. And if this proves to be useful in the classroom, you'll keep the training program. If not, you're going to abandon it. So this is that version of the paired t-test or the dependent t-test or the correlated t-test. Again, all of those are unfortunately used interchangeably. So this is one where each person provides 2 scores, a before and after, a pre-test and a post-test, and so on. So we're going to measure them before, okay, their original unaffected behavior in the classroom, their natural behavior. We implement the training in between, and we look to see afterwards if it had any effect on their behavior. Okay, so we're looking for a difference in this particular group of kids while this training is inserted in the classroom environment. So here's our data. The initial data is right here, and this is their second, so after training, their after score for this. Again, apology. Oh, that didn't even help really. Okay, so first thing we're going to do is calculate the different scores. Then we're going to rank the different scores according to those absolute values, and then sum that up. Okay, so do step 1 and 2, and then come back. So different scores, rank the different scores according to their absolute value, and then sum that column. Okay, let's see what we got. So with this, you have a different score of 10, 20, -10, 25, 60, blah, blah, blah. And then, of course, the rankings. And of course, Otto is here substituting in as the jackass sense. I do it all the time. This one, of course, had tied scores. So the idea here is you did have to deal with all of those 10s. Also, I wanted to make sure that when you're doing the ranking, you understand that if we're doing this by absolute value, the -10 has the same rank as a +10 does. So what you would have done is figure out what values these scores would have gotten. It would have been rank 2, rank 3, and rank 4, and then take the mean. So 2 + 3 + 4 divided by 3 gives us a value of 3, and then apply that for all of the rankings. And then, of course, after tied ranking, since you've already accounted for ranks 2, 3, and 4 with those 3 10s, the next score has to be a value of 5. Okay, and then going on up. If that's not what you got, This is, again, another reminder that there is still some stuff in that beginning you need to think about. So if you're still weak on the ranking, please go ahead and double check that and make sure you understand it before we get to the final homework and exam. Also, it's not in this one, but remember, if we had a difference score of 0, that would not be part of the rankings going forward. So we wouldn't have ranked anything that had a difference score of 0. Okay, now we go ahead and take our rank scores and put them into the categories of plus and minus, and then sum those two columns. So of course, that's the next place where mistakes were made or are commonly made. So go ahead and shoot those scores over into their appropriate columns, and then sum those columns up and come back and check to see how you did. Okay, so here are the scores. We only had 2 negative values. This value right here, -10, and this value of -5. So these are the only 2 ranks, this rank of 3 and this rank of 1. Those are the only ones get sent over to the negative column, the 3 and 1. The rest of the ranked scores, 3, 6, 7, 8, 3, and 5, those go over into the positive columns. So our positive scores equal 32, our negative scores equal 4. As a double check to make sure we didn't pull something from the wrong column, 32 plus 4 equals 36. Now, if you forgot how we made those decisions, we are going to be moving the values of the ranked column after they've been ranked into the columns based on whether there's a positive or negative value in the difference column. So this determines which column they go into, the difference score itself, or my cursor. So this column determines which of these 2 columns it goes into, but this is the value that we move over. So again, if you didn't get 32 and 4, please go and see which one you made a mistake on and what mistake you made. So again, if you mess up with the rankings, this is going to go wrong. If you move them into the wrong columns or move something from the difference column rather than the rank column, this goes wrong. Okay, so none of this is hard. All of it is a little bit tricky. Okay, and this is not Tim tricky. This is just easy, tricky stuff that happens. Of course, now we have the formula. And of course, as we remember from last time, there is no formula. So we're sort of stuck at that loggerheads we were at last time. We have 2 scores. We have 32 and 4. So the basic decision rules, excuse me, basic decision rules are we're going to choose the smaller of the 2 values and use that as our calculated value. And then we're going to get our critical value based on n. Remember, it's not the total number of scores, it's the total number of people. I didn't even check what the total number of people was, 8. So we're doing, as always, a 2-tailed test, alpha equal to 0.05, and then find out what the critical value is. So we have 8 individuals, 2-tailed test, alpha 0.05. So our critical value is going to be 3. Actually, I should have waited for you to do that, but whatever, I'll let you do the rest of it. Put the answer in its final format, make the decision if that's significant or not, and then interpret. Then come back and we will check your answer. Okay, so with an n of 8, of course, critical value is equal to 3. So for the Wilcoxon, capital T, with 8 degrees of freedom. Again, the degrees of freedom should always be subscript and small, so the smaller and down a little bit. PowerPoint causes also to trouble trying to get that done. So it just, it looks wrong here, but that's how it should be. So T with 8 degrees of freedom is equal to 4. That was the smaller of the 2 values we calculate. This is the other situation where for this to be significant, our obtained value, which in this case was 4, has to be greater. If it is greater than the critical value, it is not significant. If it is lower than the critical value, it is significant. So our obtained value 4 is greater than the critical value of 3. So in this case, that means that it is not significant. Again, the Mann-Whitney and the Wilcoxon, those are the 2 who have that decision rule set in the opposite fashion. So T with 8 degrees of freedom is equal to 4. P is greater than 0.05. The behavioral training program for our interpretation had no significant effect on changing the classroom behavior. So any version of that would have been acceptable. As I said in the original videos, this is one where every wheel can fly off, and even one wheel falling off, one mistake will throw everything else off. So this is certainly one to make sure you know all of those little weird chaotic points in order to do this one effectively. Sorry, went a little too fast. And then of course, our last one is the Kruskal-Wallis. The Kruskal-Wallis is our non-parametric version of the analysis of variance. So we have 3 groups or more. And of course, for all of these, we have either ordinal data or interval ratio data and something in the setup that says something has gone wrong. You doubt the reliability or validity of the measure. You have some concerns about the subject population. You, if you had a skewed sample set, you would know that. But that's the one I said not to worry about. Something has gone wrong is typically, there'll be an extra sentence in there saying something has gone wrong. But this one has 3, okay? So the last 2 were versions of the t-test. Chi-square was its own beast. This is a one-way analysis of variance. So just like the analysis of variance, 3 groups or more for us to do the Kruskal-Wallis. Okay, you are editing a mission statement, which is something Sweetbriar is going to be doing because we have our SACS review coming up. So you have a couple versions of it and you ask a whole bunch of people to rate the 3 versions, and you're supposed to see if there's one that stands out as better. And if not, your decision is just whatever one you want. But if there is one that is better, if there is significance in here, if there is a significant finding, tracking down which one is better and using that one would be the recommendation for this. So these are all individuals, so these are not the same person. These are all independent people. This formula doesn't need equal sample size, but this one has it. So that's not something we're worrying about. What we have here is our group. So this is version 1 of the mission statement, a different version of the mission statement, and the last version. And each of those was given to 6 people on campus, and they rated them on a scale of, let's say this one, 1 to 50, and done this. Okay, so step 1 is going to be rank the entire sample. Okay, again, treat it all as one big group. Don't separate it, and do 3 individual rankings. Treat this entire thing as one group. So rank the entire sample, then sum up each of those columns, and that's the data we'll use going forward. So go ahead and do that. Okay, let's see what you got. So the ranking should have been done like this. I don't think I put any tied values in here, but if so, it doesn't look like it, but if so, we would have handled it the same way we did in the earlier thing. Ranking for group 1 should have been 39, ranking for group 2, 65, and the rankings for group 3 is equal to 67. We have to determine the sample sizes, so how much is in each one. Okay, that's pretty simple. Plug into the formula, which has, again, 12 as a constant, 1 as a constant, 3 and 1 as constants. Those are all constants in the formula. It's unrelated to anything else. So if we had 7 groups and 19 people per each one, the top of the H would still be 12. Okay, it's just in the formula. Okay, so we're going to plug into this and solve. So go ahead and solve this. So 12 divided by the overall n multiplied by n plus 1. Summation of, so this is done for each of our ranked groups. In individual groups, their ranking squared divided by the number of people in that group, sum that all up, multiply those 2, and then subtract the quantity 3 multiplied by the overall sample size plus 1. So go ahead and solve for that, and we'll do the critical value step a little bit later, but go ahead and solve for H. All right, so plug everything in for H, and again, each of these has 6 individuals in it, so the overall sample size was 18. These are all the values that are put in. And when you solve for this, oh, apparently I'm going to solve it a little bit later. So we'll get to that in just a second. The critical value is, again, remember on this one, we're using the chi-square table. So again, that's that little detail that you need to do. The critical value here is based on the degrees of freedom. And I'm sorry. And it's number of groups, subtract 1 from it, so k minus 1. We have 3 groups, so 2 degrees of freedom. And just like every other example I've given, I have no idea why I keep ending up here. 2 degrees of freedom, alpha 0.05. Our critical value is once again 5.991. Our calculated value of H, which I didn't put on apparently on the last page, was 2.854. We're back to the regular rules on whether something is significant or not. So as we go back to the Kruskal-Wallis, if our obtained value is greater than the critical value, it is significant. If it is not greater than the critical value, it is not significant. So H, which of course stands for Kruskal-Wallis, with 2 degrees of freedom is equal to 2.854. less than our critical value. So P is greater than 0.05. It is not significant. And there doesn't appear to be any significant preference between the drafts. Any one of them will do. Now, if this is reality and you actually, this was something very important you needed to do, and there's no overall significant finding here, any one will do, well, you still know that there were 2 drafts that were higher than 1. So, make your decision based on those 2. It's not statistically significant, but that doesn't mean there's not data there to guide you. So if this is just research or a homework or a sort of theoretical problem, just do it the way you've been trained to do it. If this is a real life problem, you have a whole bunch of data. You have means that you can look at. Choose one that has a highest score, even if it's not significant, because there's something that caused a higher score on this, and use that to guide your decisions. Again, that's more of a situation where you have one that's obviously lower than the other 2. But of those other 2, it didn't really matter which one of those 2 you chose. Okay, one final thing. Now, I rushed through this, so this wasn't really something I expected you to catch, but I do want you to pay attention to this one thing. When you go back, and if you go back, excuse me, and look at the write-ups, the setups, I should say, setups for these experiments. I said there are two reasons we're going to worry about when using a non-parametric test. First off, if there is ordinal data or interval ratio data that had something go wrong. None of these were ordinal data. These were all interval ratio data. And if you look at the actual question setups, there is nothing in the question setup that said anything went wrong. So those are the 2 rules in which we would have used non-parametric statistics. The reality is, if this was just on homework, you should have at least questioned the idea. Why are we doing non-parametrics on this? Because there's nothing that indicates something went wrong. Now, the real thing is because these are called non-parametrics, and these are the sample questions in non-parametrics, and because I told you to sort of use these. Those are pretty good reasons to have gone the non-parametric way. But remember, on final exam day and on the homework, although I will say on the final homework, I am going to put all of the non-parametrics in a separate section. So everything will be mixed up on all the stuff we've done before. But on the final ones, I will say non-parametrics start here, and then there's 4 problems to solve. Those will have the things in it so you can identify them. But there really was nothing in these question setups that indicated anything about this being ordinal data or anything about this being a bad sample. Something, it didn't appear that anything went wrong. So as a consequence, we really should have done, if this was reality, if this was your final exam, you should have gone with the parametric version of these statistics. Now, of course, I'm being that professor again and doing something and then sort of chastising you for, I'm not really chastising you for this, but I am saying you still have to pay attention to these things. Because if you're expecting something, and certainly something would lead you to expect that these are non-parametrics, is these are problems in the non-parametric PowerPoint or walkthrough. But there truly was nothing in those question setups which indicated those things should have been non-parametric. So the correct answer would have been on all of them to do the parametric version, except for the chi-square, which you just had nominal data, so therefore you had to do the chi-square. But the last 3, there was nothing indicating something went wrong. You had worries about the validity or reliability of the data. You should have gone with the regular t-test, a correlated t-test, and a regular ANOVA. So just be aware, I'm honestly not going to try to trick you, but if you're not paying attention, I can accidentally trick you. And I know taking exams are stressful. A stats final exam is stressful. So certainly you're going to be not necessarily all oars in the water at every moment. There's always that stress and panic on exam day. I want you to be aware I'm not trying to trick you, so it should be pretty clear if you're supposed to switch to non-parametric. But you still need to know which non-parametric to go to. So so if you have something that has 2 groups and it's within design, you need to know which parametric and which non-parametric are going to be up for grabs. So certainly that decision chart I've talked about, that decision chart that I talked about in module Omega, that is something which you should be looking at. But you are going to need to read those questions, the question setups, carefully now, because that's, again, where important information is going to be there. On the final, there's really not much assistance. It's going to be a question setup and data, and all data looks alike. So you're going to need to know based on what kind of data, how many groups there are, etc., you're going to have to choose the right formula. And now it's not just a small set of formulas, it's all of them. So even though you think you've known it, so you know which t-test to use, well, you know that because you only have a couple t-tests and the ANOVA. But now when I throw in correlations and then non-parametric versions of the t-test, that decision is a little bit more difficult. So please make sure that that's part of the study. That's why I put this in here and why I wanted to run through this. Just not as a, you did bad, but be aware this is something you really haven't had to think too much about up until this point. Okay, so if the question says, what is the correlation? That's also a clue. Or what is the regression formula? That's a clue. But there are going to be some things you're going to have to make choices, so I want you to be able to choose correctly. Otherwise, you can do everything correct, but if you're using the wrong formula, it will be the wrong response in the end. So it really isn't me being sort of the asshole professor. This is watch, be careful when you're doing this, because I hate to see things go wrong for reasons that are just due to that carelessness, which is where these things tend to go wrong. So be a little bit more conscious of the things that are in these write-ups going forward into this last portion of the class. Okay, so that is our walkthrough today. There will be, again, final homework that's out today. So after the exam, you're ready and able to start with it. There is, that will be due on the 20th. Again, scanned and sent to me by a certain time, because I will post the answers, and once those answers are posted, everything is considered late after that. So I will let you know what the due date is or what the time is. This is going to be one of those 5 minutes after it is late, 1 minute after it's technically late, but you all wait a little bit till the very end to turn this stuff in. Also, on this final homework, do not wait to get started. This is a big undertaking. That's why there are no classes next week in this. This is why there are no more videos that are being posted. It's why there's no extra homeworks just on the non-parametrics. That is a big ass homework. It's going to take you a lot of time. Take that time. You're going to need it. Okay, we're almost at the end. Let's land the plane safely. I hope everything is going great, and we will see you next semester. All right, bye everybody.